Welcome to Galaxy Morphology. So the third class on this, and today I want to talk about visual classification. So we talked a little bit about that, and every time we talked about visual classification, it was sort of done by an expert. And so a lot of early science, anywhere from Charles Darwin to pretty recently, if somebody was classifying it, it was a specialist, a researcher, a lifelong researcher who generates this giant catalog of birds or butterflies or what have you. And so the same thing goes with galaxies. And so now I want to talk about citizen science, and I've recently been told that the citizen has been quietly dropped, but it's sort of crowd science. It's science by everyone, and I really like this. But we've been using the catalogs from this for science at U of L. So I'll focus on Galaxy Zoo, the one of the oldest projects that uses this. So we had the visual morphology. So that's very much the lecture one. The thing that I talked about was the Vaucouleurs, Hubble, like these were the experts of old that looked at photographic plates and classified things. Now we're going to talk about crowd classification. So we had that expert, and I always try to avoid dead white guy week. But there is always seems to be a moment where you have to sort of show that, here's a picture of what the guy looks like. So at the top, that's the Vaucouleurs, and at the bottom, that's Hubble because it's got the pipe and everything. Um, and they did the visual classifications a la this. But so it's one person looking at it, but it's one person who becomes, an expert at it. But we have a little bit of data on that where we can tell that if they accidentally classified the same galaxy twice, sometimes they sort of move one class a little bit. So it definitely depended if they had their cup of coffee, it was in the morning or in the afternoon or what have you, right? So it individual classifications can be quite consistent. Expert classifications have their uses, but it's one person and one person makes mistakes. And so if you want to get to the Hubble tuning fork, you can also, and then here at the bottom, you see Galaxy Zoo. So you can ask people, what do you see here? And so going through a website or, this is right when this got started, was right at the beginning of the iPhone 4, 3, I want to say. So smartphones are becoming a thing. So they made an app for this as well, and it became wildly popular. It's for people to sort of vote on what they saw here. And so you start with red and dead on the left. And so you do this little introduction and say, like, yeah, elliptical galaxies are red and dead. They're yellow. They don't have new stars, no new star formation. They're typically in clusters. They're typically very big. And then we have blue and star forming, less massive and not in clusters. Now, I want to emphasize that all these are generalized statements. And so a general statement means, yeah, it's true for about 90% of them. So if I encounter an elliptical galaxy, odds are it's red and dead, massive, and in a cluster. Odds are, but doesn't mean that others don't exist. And so this is the fun part. If you become an expert, you start expecting these broad trends. So you classify anything that doesn't sort of conform to broad trends as an outlier, as exceptional, like there's just one of them or something like that. So you start dismissing the outliers, you start dismissing things that don't fit those trends. So for example, if you look at the color magnitude diagram, you have smaller and dimmer, and so mass or luminosity, absolute luminosity. So you take the distance corrected brightness of a galaxy, and so you got bigger, and so both of them are massive and brighter on the right. Yes, you're seeing that on the right, and then smaller and dimmer on the left. And then I blue at the bottom, red at the top. Okay, the blue cloud are spiral galaxies, and then the red sequence are elliptical. So if you have this plot, even if you plot it any different way, like you end up with two clumps, you have a blue cloud and you have a red sequence. There's a tight grouping of red stuff, and they're all ellipticals, and there's a big blob of blue things, and they tend to be smaller and lower mass, and those are all spiral galaxies. This is the 90% correct picture of galaxies in the local universe. Both morphology, color, and mass or total luminosity are related like this. There's overlap, but this is what it looks like. So you have a mass division if you're on the right-hand side of that, you're red, dead, and an elliptical. If you're on the left-hand side, the chances are you're a blue spiral galaxy and a lower mass. And in between, you've got the green valley, which is quite sparse. Like there's a couple of green galaxies, but not a lot. And so we think those are transitional. So we have a fantastic 30-second narration of how galaxies look. You've got a blue cloud, that's where they form their stars, and at some point they stop, they rapidly transition the green valley and become a red sequence. So if you have that, you go, okay, well, and then in the red sequence they merge some more until you got the biggest ellipticals. So this is the cartoon version of galaxy evolution, and it must be holding pretty true. But if I then look at the actual data, one, there's way more scattered, there's way more overlap and spread. And then if I then add Galaxy Zoo, where people are not biased because they've looked at a whole bunch of galaxies already, so they're not predisposed to, as they see something blue, to say, oh, that must be a spiral galaxy. Now, this is ancient.
Hurting Helen agree.
Yeah, you have to get the sales early. Yeah, it's a real jungle out there unless you're wily.
If you're wondering what this is,
Hurting Helen agree. Great minds think alike.
it's ancient. It is a very, very old skit from Kids in the Hall, which is a Canadian. I'm not Canadian, but I have people who love this show. So yes, all great minds think alike, or fools seldom differ. Both of them are sort of the same coin, right? So if instead of asking a single person to classify all galaxies, why not ask 30 rather random people? This was the 30 Helens, but you can also just think of any random 30 people on the internet. And this is back in the day when we thought the opinion on the internet was a good thing. And so we asked them all to classify this galaxy. Is it a spiral galaxy? How many arms do you see? Does it have a yellowish bulge in the middle? And then look where the majority goes with. And so is this an elliptical? Do which kind of E0 or E7? And so you can sort of train people minimally and then ask for their opinions and then average everything out. So you get an average. So if everybody agrees on this, 100% agreement, it's an E5, that's it. There's no spread either way, then you're like, I'm pretty confident it's an E5 and I don't have to put an error bar on that. Can you see this galaxy edge on? Is this an edge on? And if people see this, they go, yes, it's an edge on, right? So you can go through all these images. These are, the prettiest image I can find, but you can also go through fuzzier images, smaller images, loads of images, and it's a very rewarding thing. It sort of presses the reward center in your brain because you're helping science and you're seeing new things, right? There's a reason this is a satisfying thing to do. And if you're, done with it, then you move on. So going through all these, do you see a ring? Do you see a dust ring? Can you see this edge on? Is this sort of edge on? Is this an elliptical? Is this a spiral? Do you see structure? So what you then see suddenly, red spirals. There are galaxies that look like spirals that get classified by everyone as a spiral galaxy, but they're red. And they're elliptical galaxies that are smooth like an elliptical galaxy, but they have blue in them. So they're bluish, they're blue throughout. So like I said, 8-10% of all spiral galaxies are red. And 8-10% of all elliptical galaxies are blue. So it wasn't as clean as a divide as we, did with our cartoon story. So I like the pitch here. Like this is a different kind of science. So part of the science here is sociology. How do you engage and keep a group of people that want to help, but how do you engage them and how do you keep them engaged and not lose them effectively? And so first thing is like, for you have witnesses what you're about to see. And this is true because we've taken, a deep image of the night sky, but a Sloan Digital Sky Survey or some of the later surveys that we've been doing, KIDS, DESI, you name it. And so we looked at them, but at some point this becomes a pipeline. Nobody's scrutinized every galaxy that comes out of it. That's what you're doing right now. And so breaking it down into simple multiple choice questions is this an elliptical? Is this a spiral or structured galaxy? Or is this an artifact, right? So is this an actual thing that snuck into our catalog for no reason? So you get that first question, you then go to a different one, but how do you keep people doing this? So
you're all individuals. Yes. You're all different. Yes. I'm not.
So classification by crowd consensus, right? So if everybody agrees, or almost everyone agrees, that this is an elliptical galaxy, it's probably good to classify it as an elliptical galaxy. If it's 50-50, then you've got something that might not fit in either category or is, unresolved. So you actually know how confident you can be in your classification because you've got multiple people agreeing on this. Life of Brian, I mean, you'll have to excuse me, but that is a classic. You may have seen Life of Brian back in the day or heard of the troupe Monty Python. I just thought of the group consensus. I thought of this scene where they all agree vocally, right, as that they're all individuals. But as a group, we actually work really well as a humans, and the human eye works incredibly well as a group to sort of classify these things. So you get things like these spiral galaxies, like those things in the middle. That's a spiral galaxy, but it's not blue. It doesn't have star formation right now. That's very strange. You look at that in detail, it does have an acersic profile. It looks like a flat disk. Those are spiral arms, but they are not blue like the one on the left. And it's not an elliptical on the right because it clearly has a lot of swirly detail. Okay, so if we see unusual things like that, if we see a single one, like an expert going past this and sees like, oh, look at that, they might just try to cram it in or try to skate past it because it's the one time that they see it. But people who are literally coming at it fresh might identify this like, yeah, that's a spiral. Okay, cool. And then you end up with a crowd consensus that, yes, that is in fact a spiral galaxy there in the middle. And we found more of them, like they're not that uncommon. We saw a similar thing with three-armed spirals. So every time I saw a three-armed spiral, I would go, oh, that must be an exception. And it sort of is, but it's again a 10% exception. That's a viable path for a galaxy to look then. That's not a, oh, that one has just had a little bit of a tidal interaction or something. So Galaxy Zoo started with the 250,000 galaxies and asked more detailed questions. So they had a first one, they had a second one. I think we're on Galaxy Zoo 5 now. But it gives you an idea of how old this is, especially in internet terms. Think internet 2008, 2009. Could anybody even remember the internet back there? Like Twitter's maybe a nascent thing, that kind of. And so part of the reason that this was so popular is because the website worked. You could instantly do it. There was an almost immediate community of people that were working on this with professional astronomers, and so there was sort of a forum. You can sort of see there's a forum button. So there's a forum where people would post links to odd things, or if they had a question and go like, hey, is it okay that I see spiral galaxies that are red? And, then have a professional astronomer jump in and go like, yeah, no, that's fine. Just classify what you see. Or, hey, I see this really strange things. Could you take a look at that? And also the second part is that Brian May, of the guitarist of the band Queen, that I sincerely hope you've heard of, he is an astrophysicist, and on the nascent social media tweeted like, hey, I'm doing this Galaxy Zoo thing, it's cool, everybody should check it out. And the, I don't know, quadrillion Queen fans immediately sort of went here, and a lot of them stayed. So you have a very large pull for people, and so this became quite popular. So this is an idea of what the series of questions. So one of the underlying challenges with this kind of thing is to keep people engaged. Maybe not the whole time, maybe not their entire work day, that would be bad, but keep them engaged for while they're doing it, because if they leave, if the server is down, people leave and never come back. If they enjoy doing this, they do it for 5 minutes, they do it for 5 minutes again the next day. This might just replace their phone game. And so the questions are organized in a way that if you say, yeah, it has a disk or it has structure, that you then go to questions about that structure. But if you go, no, it's an elliptical, then you just are asked, how rounded is it? And then it goes, is there anything odd? And I know for a fact that the people who designed this, that one button, is there anything odd, they are now wishing they never put in. This is the Galaxy Zoo 2 interface. That odd button has been removed and basically goes to the odd features, and nobody uses the word odd anymore because odd implies a implies that you have an expectation. Odd means you had an expectation going in, it wasn't completely met, and then you go, that's odd, which means that you had that you're sort of applying your biases, your predispositions onto the question, and then go, well, is it odd? And if you were expecting it, well, then it wasn't odd, right? So it's a value judgment. It's sort of you're asking people about their expectations, not with what they see. And so that's unfortunate because one of the things I wanted to do is, well, like, do I see a dust lane? And so we'll get to that, I think, in a minute. But part of that is that you then also can look at other things like you have color and you've got disk galaxies. But not only that, you've got, if I, let's follow the green line, like, yes, it's a disk galaxy. Can this be viewed edge on? The answer is no. So it's not edge on, it's face on. Okay. Is there a sign of a bar feature through the center of the galaxy? Great. That's a follow-up, right? So I have galaxies that are disk galaxies that are red. So they're in a particular corner, right? People vote that they're disk galaxies and they have a red color. And then I could look at how many bars are there. And if I then look at the blue ones where people voted that, yes, they are disk galaxies, same thing. Like I can say 90% of people have to agree that this is a disk galaxy. And I can look at the same question. Is there a sign of blue of bars? And so you can say if 30% or 90% of people agree that there's a bar for both the blue and the red galaxies. Where are they? The red galaxies have way more bars. Huh. Bars do something to your star formation, or star formation does something to your bar. One way or the other. But this is how you can do classical measurements like color, classical measurements like mass or luminosity. So you take things that we measure as a matter of course, and then combine that with voting from the Galaxy Zoo. And this is a very powerful combination because now you can say, I've got this morphological feature and it's correlated with this, which means that if I have a scenario how bars form, it has to do something to the color as well. Not always. I mean, I can still have a barred galaxy that's blue, but there's about twice as many galaxies with bars in the red end side than there are on the blue end side. So Karen Masters, you see here at the bottom, she's going to be our bullet lecture this October 10th. And on October 11th, she's going to talk about Galaxy Zoo. She's one of the pioneers of this, absolutely fantastic researcher. So, I invite you to come and have a look at that, or at least look at the video. I'll post that as well. So this is the kind of research that you can then do. And the neat part is as soon as you have a catalog, you can sort of formulate new questions like, well, I've got this color, blue and red, like GR, that's one color, but you can also go for U minus G, like I can use a different color. I can use bars or I can use bulges. I can use, instead of bars, I can use bars and luminosity or things like that. So I can actually go for follow up on this even more detailed. Now, I love this fact that Galaxy Zoo is not just astronomy. It is astronomy. It is absolutely perfect science for astronomy. It is really fun, but it is also a sociology experiment. Like, why are we doing this? And so there is exploring the motivation of citizen scientists. This is the sort of the reaction of people. Like, why did you do this? I wanted to contribute. This is a fantastic thing. If you're losing faith in humanity a little bit, the fact that so many people go, I'm here to contribute. I like the astronomy. I like the discovery. I like the beauty of the whole thing. Just, I am enjoying this and nothing, this is why I'm doing it. Fantastic. Like that's the kind of votes that you want to see. And the fact that it's quite equitable, right? Everybody can contribute to this. So this became like a Zooniverse, right? It became a universe full of these different projects. So you can small and large projects, people, the kind of thing where you need people's vision to help you really make a judgment call. And people are really, really good at that. You can sort of think that at this point, machine learning is good at that, but guess where machine learning learned some of this stuff? And so you have things like, do you see animals on these nature cameras? Can you help us transcribe the longhand from all these historical documents? Can you help us find exoplanets in time series, right? So there's a whole bunch of different people-powered research, and I like this people-powered research because it's also an outreach program. Everybody can be involved immediately. So there's a Galaxy Zoo Hubble version, right? There was so many Hubble pictures you can actually look at the visual classifications there. And now as of a week ago, they are classifying the Euclid Zoo. The Euclid is a new space telescope launched by the European Space Agency. Um, I have a weak spot for the European Space Agency. I worked there for 3 years, and the Euclid people were just down the hall from me, and they were patiently getting ready for basically this moment to get their satellite up and running. And Euclid is going to take a picture of basically Hubble resolution in the near infrared of the whole sky. And so we'll have loads of pictures of nearby galaxies and far distant galaxies that we can see all the detail in. And so I'm very curious what's going to come out of this. But this is already one where people are classifying, but then some of underneath it helps train something that is a machine learning algorithm called Zubot. And so Zubot is sort of is learning from people's classification and then going, well, that picture looks exactly like that picture. So that classification also goes for similar pictures. So it actually helps speed things up. But the entire night sky would take us a very long time to do. So Galaxy Zoo data releases now with visual classifications of anything observed by Hubble, James Webb, and soon Euclid. So we can have quantifiable morphology for galaxies. So we can actually say high probability, low probability of a bar, both near with Sloan and the other nearby surveys. And then now with Jada Bastine, soon Euclid, we can go halfway across the universe and look at the morphologies there. So you can have a question that's like, hey, how common are bars, for example, but out to much greater distances. So these newer catalogs, DES, KIDS, Gamma, etc., can be ingested and evaluated. So I'm part of the Gamma collaboration. So that's where a lot of these undergrad research projects that I come up with are in, because we have the Galaxy Zoo classifications, but you also have accurate star formation, actually stellar masses. You have other classifications like, hey, is this in a void? Is this in a thin tendril? Is this part of a group? So you have environmental information, you have classical properties like stellar mass and star formation, and then you have morphology from Galaxy Zoo. So these are the fun things to then cross-correlate. You can even do fake galaxies if you've got good enough ones, although that one was the hardest to do. Again, remember, you also have to keep people interested, and the illustrious ones felt fake. You can't tell people this is fake data. They hated that, right? So they did a separate illustrious fake galaxy. Like they were like, oh, let's try that. And essentially everybody walked away from it because they're like, yeah, I'm not doing fake stuff. I want to see the real thing. So sneaky, they sort of slid that in. They slid the occasional illustrious galaxy in order to get classifications in the same way, to see if the morphologies looked good enough, if we understand how this works well enough that we can reproduce it in a computer. And then there were even more detailed questions, things like, hey, do you see lots of globular clusters? Or identify where you see the spiral arm, like actually follow this along. But it's also, and this is sort of happening underneath, training for the Zubot machine learning algorithm. So a lot of the early Galaxy Zoo classifications became machine learning challenges. And so the DR1 to the first data release of the Galaxy Zoo, which had only a few questions, it was based on images, that became the first challenges. These are called Kaggle challenges. I'm not sure if I pronounced that right, but they are challenges for people to learn how to, like, how good do you do them? Because you sort of you train on a part of it, and then there is a sort of part that's left behind that's sort of in the envelope. And so you go, okay, what are your predictions? Okay, well, here's the data set that was in the envelope. You now have to predict how well you do. And then we know the answers because we've got the classification from people. And so you predict the fraction of people voting for this as a bar, or the fraction of people that says this is a spiral galaxy based on images. So it's been a really, it's an interesting combination of fields where you have a little bit of sociology happening. There's definitely a lot of astronomy happening, and then there's now also machine learning algorithms that are being trained on this. But all this data is available. Galaxy Zoo 1, 2, the Hubble Zoo 1, and the Gamma is now also will be available very soon. So all of this is appearing on here. The tables are available, the images are available. So that's what you can start to do. So you can do statistics on this, right? So it feels like, oh, great. So I can see how common a certain morphology is, or how common three-armed spirals are. But that feels like that's very broad, right? That's all over the whole population. Statistical evaluation are great. That's the main scientific return. But you can also find something really, really weird. And with this many people looking at it, just looking at it, and also looking at it and coming from it with a fresh perspective, they find some really, truly rare stuff. And so here's the first example. And since I'm Dutch, this never ends to tickle me, because this is Hanni van Arkel is a elementary school teacher in the Netherlands. She is a massive Queen fan. So this is how she ended up on Galaxy Zoo. So she started classifying things, and she found the thing on the left. And she said, what is this voorwerp? What is this object? Voorwerp means object in Dutch. So very quickly, the the English speaking astronomers sort of called this thing a voorwerp. And this has a very long tradition of people not quite understanding what the other person was saying. There are plenty of places here in the US that are basically the natives' tongue for that's a mountain. And so you've got mountain, or, the Gobi Desert. Gobi means desert, so it's the desert. Or the River Avon in England. When the Romans showed up, they were asking the locals, what is that? And they said, river. Avon means river. And so this is a voorwerp. This is a voorwerp object. It's an object, but that blue thing, that Smurf looking thing on the left, that weird little loop, if I would have seen that as a professional astronomer, I would have looked at it and went, oh, that's funny looking. But very likely somewhere in my brain, since I've looked at a lot of objects and a lot of them have some odd reflection in the telescope, or, the chip was misbehaving, or this was a bright thing. So just before we took the blue picture, we looked at something bright and then moved around a little bit, or I don't know, a technician with a LED lamp. Anything but, oh, that's a real thing. But if you come in fresh, like you literally come straight off Brian May's Twitter off into that thing and go, huh, that's weird. What is that? I'll go ask on the forum. So people looked at that and went like, yeah, that is in the blue filter and nowhere else. And it turns out it's an oxygen cloud. It's just oxygen. It's just there, and it's only emitting in the blue. And so on the right-hand side, you see the Hubble picture of that, where that particular channel is now the if you make a color image, you take a red channel, a green channel, and a blue channel. And so it depends a little bit on what your reddest wave picture is and what your bluest picture is, and then the green picture. So the green is now the oxygen, and you can see, yeah, there's this weird loop, fantastic shape there. And the Galaxy Zoo scientists figured out what this was. Like, that galaxy at the top has an active galactic nucleus, and you can sort of see it's a little inclined. So there is a jet coming, or was a jet coming out of either pole of the center there, and it hit this cloud and ionized it just yet, and it's now quickly radiating that energy away. Here's the funny thing. This isn't going to last longer than 100,000 years or so. So this is an incredibly short-lived phenomena. We would have never picked it up unless somebody who was not had a predisposition towards like, oh, that's probably an artifact, hadn't asked. So, and this was the only example for years. There's only one of them because it's going to fade away very quickly. So it is a very transient thing. Um, some others have been found in the meantime, now that we know what to look for. But yes, 4-Web is now a class of objects. I'm again cannot laugh enough about this, but and it's a rare thing, right? So you can find incredibly rare things which tell you that there's an AGN and just switched off, like it did this recently was active, ionized that cloud and stopped. So you have things like this where you can follow up like, hey, I'm seeing an elliptical, but it has this swirl. Let's check it out. Oh, there's star formation happening in the center of this. You see something like this where it's like, well, what is that, right? So a lot of people came back to the forum with like, I am a little stumped. And every time that happened, something new and interesting popped up. So you get things and you get whimsical names, and I love this, right? You put a crowd of people on this, and they start making whimsical names for all these fun galaxies. And so you have three birds, E.T., the elephant, the dolphin. I think that one that you see is the penguin galaxy, and that has just taken. Oh, I should have put that in there. Sorry, I should never mention the notes that I'm taking in my head, but there is now just a picture from JWST of that penguin galaxy. So there's a Hubble one and there's a JWST. So I'll stick that in for next time. Um, and so yeah, these are rare, odd-looking, pretty-looking. And so these are things that are interesting enough to go follow up, right? Or just take a fantastic picture of. So what can the zoo do for me, right? If you can have a question about galaxy morphology and you can find serendipitous objects, serendipity meaning um, pure dumb luck, right? So if you need a pure dumb luck to see the thing, then yeah, having 300,000 people look at all the pictures, they're going to pick up on a lot of them. And so you provide a training set for future galaxy morphology learning because we're expecting more and more data as it comes in. And so we can have something that is good as the Galaxy Zoo. Now, here's my very first foray in trying to do science with the Galaxy Zoo. I like edge-on galaxies and I like dust. I like that stripe of dark dust in the middle, and I'm curious how often it happens. So I can say, okay, I want all the spiral galaxies. Oh, if you say it's going to edge on, I'm like, yes, I want that to be edge on. Then I go to the anything odd. Do you see a spiral? Do you see a dust lane as well? Now, here's where that button really tripped me up because a lot of people would go, it's an edge-on galaxy. It's supposed to have a dust lane. So they would go, do you see anything odd? Nah. And they move on to the next. So there aren't that many votes for dust lanes in edge-on galaxies because a lot of people don't think of them as odd. So almost good. But you can look at instead of relying on a single expert, you get 45 people on average looking at this. And so you can look. This is from Julianne Del Canton back in 2004. She noticed a trend, but this is based on like 24 galaxies. She noticed that in big galaxies, there's like this big color gradient. So there's a dark stripe in the middle, and small galaxies don't have that dark stripe. And like, do I see the same thing happening in all my Galaxy Zoo, like the fraction of ones that are edge on, the fraction that have a dust lane, and yes, exactly at that mass, you see it sort of pop up. There's more dust lanes starting to show. Okay, so what kind of student projects did I do? I'm just going to advertise these. So Dominic Smith in 2022 did green galaxies. He looked at the Green Valley and it's like, hey, do they have anything that is odd compared to their blue brethren? And he was like, yeah, they have more rings. So it's either that if you go into the Green Valley that you develop a ring, or you already had a ring and as you fade that becomes more prominent. I mean, it's a little unclear which mechanism is the driving one here, but the observational fact is that if you go into the Green Valley, more rings. Ren Porter Temple, they looked at the number of spiral arms. So if I have more spiral arms, am I better at making stars? That's a good question. And since gamma has very accurate stellar masses and star formation, so all the error bars were pretty small, you can actually see that there was a trend. And there's a very broad trend, but it's like, yeah, there's more mass, there's more star formation as you go, add more spiral arms. But if you do relative growth, so the star formation divided by the mass. That's called specific star formation rate, or just basically the percentage growth. The more arms you have, actually, the worse you get at making new stars, relatively speaking. It's like a small galaxies with, or sorry, a galaxy with only 2 arms is adding more stars relatively to its stellar mass than a one with 4 arms. So that was fun because that was not something we knew. And Laurie Porter looked at the galaxies in the void of space and noticed whether or not they were disk or spheroidal, and they are dominated by disk galaxies. There are a few ellipticals, but they are very rare. So most of them are disky galaxies, which is not unheard of, not too surprising, but this was the largest sample of void galaxies that people looked at. So spiral arms, this is the number of spiral arms. I like these plots. These are called violin plots, where you take a histogram, but basically put them on its side. And so if it thickens, that's where most of the data sits. But you can also see if there's like a tail in one direction. So as you can see here. So you say, okay, I'm putting a threshold. I need at least 30% of the vote for this number. Then it's that number. It's like it has 1 spiral arm, 2, 3, 4, 5. You can see the numbers at the top. So most galaxies have 2 spiral arms. Most people say for most galaxies, there are 2 spiral arms. That seems to be the most common mode. But I want you to notice that 3 is basically the next 10% of that. 1 is 10% of the sample. And so you got about 1,000 with 2, and then 100 on either side, and then you still got a few with 4 and even 5 or more. And so stellar mass goes up a little bit. You see the median goes up, but also like you see sort of the balloon move upwards. So by the time you get to 4 or 5 spiral arms, you're talking more massive galaxies. If I then look at star formation rate, the same thing goes, like a little bit more star formation rate as I go along, long tails in some cases. But then if I look at specific star formation rate, the relative growth, I'm seeing that the whole thing just sags a little bit as I go from compared to 2, for example. It's a little more on the ones, and then 3, 4, 5 are a little lower and lower. So relatively speaking. Another thing that you can do is looking for overlapping galaxies. And so this is a chance to really shine, because those are things that are considered incredibly rare. How rare? Well, take this example. It looks a fantastic picture. It was taken with Hubble. It is by sheer coincidence that we found that, because I was at a meeting, an American Astronomical Society meeting, and there's this I've sort of run into a colleague, Julian Del Canton, in the hallway, and she goes, "Have you seen Bill anywhere? Bill Keel?" I'm like, "Yeah, he's around, but I haven't run into him yet." And she goes, "Oh, you like this too." So she showed me this like first draft of this color picture, because it happened to be in her Hubble picture. You see all those stars around it? That's the galaxy she was actually looking at. She was looking at the individual stars that belong to a completely different galaxy, but she found this just at the corner of one of her pictures. This analysis was always limited by known samples. We knew way too few of these overlapping pairs. So back in 1992, 1993, the idea was to look for those, to use the foreground galaxy, so they use the background galaxy as a light source so that you can see the dusty structures in the foreground. Anecdotal pairs, this is literally all the anecdotally known pairs of galaxies, whatever your colleagues told you at a conference. 15 pairs in total. A few of them are follow-up with Hubble, so these are individual papers doing one of these, right? 3 pairs total. Then we do a spectroscopic search to see if we can actually find more of those pairs. You find about 80. Most of them are really itty-bitty, can't really do anything. Once again, we only have one that I just showed you. Again, 1 pair that we do a bespoke analysis on. And then in 2013, so 10 years ago now, Bill did a galaxy zoo, like essentially threw onto the forum. I don't know, I don't think it's called a forum these days, but basically the chat box, the chat group, hey, if anybody sees an overlapping pair of galaxies, let me know. This wasn't a question. This wasn't a button. Just to be clear, nobody had to press a button. You'd actually had to go out of the thing that you were doing and put on the forum, hey, this number, or, this position, here is where I saw an overlapping pair. So This is supposed to animate, and it doesn't show. So with Galaxy Zoo, these are hard to find otherwise. They're blended. They're often the same thing in the catalog. They're not actually have separate catalog entries. 2,000 of these things were found by the Galaxy Zoo. The catalog paper is in 2013. We're now working on a second one. In fact, I was hoping to work with Ian on a follow-up catalog this way. And so we've been following up with Hubble, HST, and JWST. So with Galaxy Zoo, the classification is based, now we have an additional classification like, hey, how do these two galaxies overlap? Spiral, spiral, face on with an elliptical in the background, for example, those are the best. Two edge-ons, you have all these weird configurations, so we have this shorthand for that. But what you can then do is see how transparent the foreground galaxy is by just assuming that you can flip the background galaxy. And you get a transmission. How well does light transmit through this galaxy? And you often lose anywhere from 0 to half the light, or 100% of the light sometimes if you get to the center. And so the galaxies are sort of semi-transparent. I'll do a little sidebar here because I'm already at 40 minutes, but I'll do this very, very briefly. You may have heard of Vera Rubin, the discoverer of dark matter, at least on this side of the Atlantic Ocean. I visited her institution back in 2005. My PhD was on the central question was, how transparent are spiral galaxies? And she goes, oh, cool, yeah. And so she just rummages around in this massive library behind her and goes, here's a letter from Hubble, the actual Hubble, to a friend saying, hey, I saw a little galaxy through Andromeda. I don't think it is as, opaque as we think it is. So this was a question back in Hubble's day, and we were trying to answer it then, and now we have a way to do it, in quite good detail. So this became a star smog HST, so the Hubble Space Telescope program. And this is the most convoluted acronym my brain has ever produced. The starlight absorption and reddening through a survey of multiple occulting galaxies. It's now been a while, but we have about 50 of these have been observed. You're going to like, what is happening with the Swiss Army knives there? So dust happens to do a lot of things in galaxies. It's a catalyst for star formation. It is a way to hide metals. It's a way to use it for chemistry. Like there's a lot of things are happening on dust, and it's a really important, for its mass, which is typically like 1% of the whole galaxy, it's doing a lot of things. So I can think of lots of science cases to do here, and I think of that particular not very useful Swiss Army knife. So if you want to actually get time on Hubble, or you want to get time on a proposal, instead of trying every possible use case for your data and what you want to do with it, make sure that you tell them like one thing. This is the killer application, the corkscrew in this case. Like, it is the supernova. We need this for this. And so we got all these Hubble pictures. These are short snapshots of various overlaps that are nearby. And as you can tell, some of them are, good overlaps. Some of them are sort of like right at the edge, and we can't tell as much. We sort of got what we got, right? You couldn't put in a priority list. So it just was like, here's a list of these things. You're going to get what you're going to get. But we got quite a number of good ones. And I want to emphasize, for example, that we selected the top two, but realized that there's now a small dwarf galaxy that has all that dusty structure around it. So that's pretty neat. And we got this guy. So we got a face-on spiral galaxy with an elliptical in the background. So that became sort of here's a fantastic example. VV191, Clayton Robertson is now finishing his PhD, and I think 90% of his PhD is going to be on this pair, because you can look at all the dust in there, you can look at how much of there is, so you take the elliptical galaxy in the background, you know what kind of profile, it has a divocular profile, so on the flip side, it has to look like that underneath all that dark structure, so you can estimate how much light is missing. So you can directly measure pixel by pixel how much extinction there is. Okay, so that's what we've been working on. We've been following that up with the James Webb Space Telescope. Just to answer one more thing, who has time for this? Well, back when Angry Birds Angry Birds came out at the same time. And so that gives you a nice comparison sample. Angry Birds isn't scientifically useful. It is just, made into a movie. About 200,000 years were spent on Angry Birds, 300 million minutes a day. Meanwhile, this is the list of almost 200,000 volunteers on Galaxy Zoo who didn't play Angry Birds, or if they did that in addition to doing Galaxy Zoo. It was sort of their Angry Birds. So many different more survey data is becoming available. Galaxy Zoo keeps classifying. The science questions keep changing. We answer one, a different one, or multiple ones pop up. So Galaxy Zoo version X, we just saw Euclid. There will be others. So these are sort of like all the different question trees that have happened in the meantime. The central one is the one that I've been using for Gamma, because that's the one that's been used there. But as you can see, just from the different arrangement of purple and questions, etc., some data we asked different questions than we did on other, and so it's sort of unique data in each time. This is what we've got from Lee Kelvin's paper in 2018, and then Dominic Smith followed that up and did it again, but now with better data altogether. Okay. Yep, I have about 5 minutes left. You kind of go like, oh, what's this? Well, this is just Andromeda. And I like this example as well because Andromeda is a single galaxy. And back when I was doing my PhD, you're trying to sound clever and say like, okay, well, here's sort of the limits of what we probably can do. And one of them was, well, you can see those background galaxies through Andromeda, but you would need to do just a stupendous big chunk of Andromeda to get enough of them to actually tell how transparent Andromeda is on average. Because it gets really hard to identify them because there's lots of resolved stars in front of them. So it's called crowding. And so you can barely find the background galaxies just because of all of Andromeda's stars sort of crowding it out. So I think one of my predictions essentially was, yeah, Andromeda would be a good place to do it, but you would need to cover so much area that no sane Hubble time allocation committee would go for it, right? There's no way they'll go for that. Well, Julian Del Canton didn't read that part. So as you can see, this is a good third of Andromeda taken with Hubble. Like these are all, you can see that it has a weird shape, right? This is not because it's not a single snapshot. It is carefully tiled pictures with Hubble, just 600 of them, I think. Like there's just one after the other and have them all sort of overlap enough so that you can get the whole thing as one giant mosaic. And all of these little stars, every single component here you can resolve the stellar population out. So Hubble imaging, so this is what that looks like. You see the two cameras, one of them like this, the other one like this. And so you have to sort of very carefully move Hubble as you go through. And so you end up with these bricks and then so fill these in and then you end up with, and it was called the Panchromatic Hubble Andromeda Treasury. And so that was a new Hubble kind of proposal where they went like, okay, well, suppose Hubble dies tomorrow. What are we going to be kicking ourselves over if we don't do this? And of course, having a good chunk of Andromeda actually imaged to this resolution, that's a good reason to do it, right? So, but as a result, like we had this massive mosaic, absolutely one of the biggest pictures in astronomy we've ever taken, especially from space. And we've got all these resolved stars. And so that's a star cluster, but machine learning, especially at the time, was quite bad at identifying that clump of stars as a star cluster. But that's great for, again, for citizen science, for getting everyone involved. So you also find background galaxies. So you have people who basically draw a circle, say, that looks like a background galaxy to me. That looks like a background galaxy to me. That looks like a star cluster. The main science question was, is that a cluster? Can you find the clusters for us and then also mark off anything that looks a little fuzzy, but that's not something that we're looking for? Now, I want to emphasize here, my entire PhD, 1 full year of that was looking for, in Hubble pictures, background galaxies and counting them. And it took me a full year to do that. This group of people did everything in a couple of weeks. So they went through all the star clusters, identified all the background galaxies, and did it in a few, this is in 2 minutes, but it's still, yeah, they found just as many background galaxies as I did in a year, and at a cost somewhat of my sanity. And meanwhile, people, if they agree, everybody draw a circle around it. That's definitely a cluster. If just one person did it, you're going to go like, I'm not so sure. So you had a confidence level of how many of these clusters there are. So star clusters, background galaxies, here it is. You've got your catalog. So you can get to work. You can look at the star clusters in Andromeda. You can look at their properties, look at their stellar components, look at how many stars each of them have. Where do people draw most circles? That's sort of the good edge. And then you've also got a catalog of background galaxies, should you want to do something with it. So you can actually look how transparent Andromeda is based on those counts. So, citizen science. Do you got hundreds of objects? You're better off doing it yourself. You don't want to train other people. Got a couple of thousand? Ask your friends. Do you probably have a small collaboration? You can set something up on Galaxy Zoo on the Galaxy Zoo server, but it's better to have, a small group classify it. However, as soon as you get over 10,000, ask everyone. Go for a full public project. But 90% of this effort, and what I just showed you, right, that was the 3 weeks, was the last 5% of that. Up until then, a lot of that was testing the server, make sure that everything ran smoothly because you only get one shot at this. You make it public, everybody flocks to this project, checks it out, and then gets a 404 page not found. They will never come back. So you'd either work smoothly or not at all. It's sink or swim here. It's fun and different. So the data is, but it's still data. So you need calibration. You need to occasionally, if you have somebody going through, you saw that like somebody was going through and just clicking on all the yellow things. I was like, no, that's not what we asked. So you have to sort of take that person out. You have to sort of gently remove that from the data. It's the future, but also it's the training for machine learning. It's the validation for machine learning. So I just finished a paper, and some of you were on it, with where I take 2 iterations of the Galaxy Zoo and see how much they agreed. One of them is full, people. The other one is people plus ZooBot. And so, hey, how much do they agree? And they agree quite well. So it's a good, fun, but also good science. So rich data set, quantification of morphology, lots of interesting data mining projects to do, different versions answer different, more specific questions. So if you go like, I wonder about clumpiness, there was a clumpiness project. It's easy to set up new and interesting galaxies. You can set it up, and so people have done this for example, with a class that they just all classified these. Other science applications are the Zooniverse, so very much biology, sociology, you name it, there was a science that has used the Zooniverse. It's great for labels for machine learning. So if you like machine learning, or as we are now prone to call it, AI, yes, image recognition is trained on this. There is a very, very important reason that this is attractive for people who do machine learning. It doesn't involve people directly. It's not, if we get a galaxy classification wrong, it's not the end of the world. This is the kind of thing where if you're using machine learning to do something important where people's lives are at stake, yeah, then you want to get it right. And so this is a good way to train on something that is a low stakes as far as um, human experience is concerned. I mean, it's not great, but you can fix it. And so the unpredicted benefit, right? The serendipitous discovery of very rare objects and phenomena, like something that you wouldn't have found any other way. This is the way to do it. So, yeah, any questions? Sorry, I went a little long because this is something that I use quite a lot.
I don't have any questions, but I did go on to the new Galaxy Zoo Classify thing and tried it, and it's a lot harder than it seems.
It is. There's a little bit of training. Okay, so you can take us through it at some point. There is definitely some hardcore members at this point. They have actually gotten onto scientific papers and what have you. But I quite like the original ones. But this was also sort of the early internet where apps were just a thing, and your phone isn't the plague of your life. It's just a new shiny thing to play with. But it also helped. Yeah, it helped a lot of things answered. So I think I like getting people involved with science, and this was a great example. But I'd love to see how easy it is to classify now. Any other questions about Galaxy Zoo? I think, Alexia, you're going to play with DESI data on Gamma, or no, on Laduma, right? Okay. All right. So this is a very useful tool, and there are definitely more projects to be done here. And so I all encourage you to go to the colloquium. So this will be on October 11th by Karen Masters at 4 p.m. So she'll talk about Galaxy Zoo results, the latest and greatest, right? Stuff that I don't know about yet, and I'm very excited to go hear about. And so, but it's a different kind of science where the tool is now a crowd of people. And so you have to deal with people. This is just the way it is. But very enthusiastic, very happy to contribute. And the community sort of grew around this. So I really like that component as well. Okay. That's the background. That's Galaxy Zoo. So that tells us more about morphology. It tells us detailed questions. And I really like the fact that we're no longer relying on that one guy. We actually have an error bar. We have an uncertainty on, that question, like how much spread is there, or did everyone agree, or is there a little bit of a minority report? So I like that part as well. So yeah, there's this is how we do a lot of galaxy classification these days. I will see you all on Thursday next week. I hope. I may have to cancel depending on circumstances, but if that's the case, I will let everybody know in time. Otherwise, I'll see you all for part 4 next week. Yeah? All right. Talk to you then.
See ya.
Thank you.
Oh, are we meeting tomorrow
Yes.
for research-related purposes? And that's at 11.